Bismillahirrahmanirrahim. Uh, in today's lecture, we will talk about different biasing techniques. So before that, I will just review what we have seen in the last class. So in the last class, we have seen the transistor circuit like this, okay, and it is having a power supply which is VCC, and this is ground, and you can see there is an RB, there is a VBB, right? And we have seen how to analyze this circuit in the last class. So we will be taking a loop at the input side, we will be taking a loop at the output side, right? And we have seen how to write the Kirchhoff law at loop 1. So let us assume we are considering loop 1. Now at loop 1 you can see this is loop 1, actually this is loop 1. So if you are writing the Kirchhoff law, it is minus VBB, and you can see that the current is going inside, so this is plus and minus VBB plus IBRB, right? And the base emitter voltage whenever it is forward biased is 0.7, so plus 0.7 is equal to 0. So from this equation we have IB is equal to VBB minus 0.7 over RB. Now we can see what is the situation at the output side. So at the output side we have another loop which is loop 2, okay. So I am writing the Kirchhoff law around loop 2. Now if I am starting from VCC, this is minus and this is plus, so it is minus VCC, and you know that the collector current is going down, right, into the collector for NPN transistor. This type of transistor is NPN transistor. So you can see that whenever the current enters, we have plus then minus. So plus IC into RC, then the current enters, this is plus, so VCE, so plus VCE equal to 0. So VCE is equal to VCC minus IC RC. Now how to find this IC? The IC can be easily found by using IB. IC is equal to beta DC times IB. So this is a kind of bias, actually biasing technique that we have seen in the last class. So what do you mean by biasing technique? Biasing technique means applying proper voltage to the transistor in order to select the operating region. So you know that the transistor is having different operating regions. So operating regions in a transistor include the active mode, that is different modes of operating, different modes of operation of a transistor includes the active mode, then the saturation mode, and the cutoff mode, right? This we have discussed in the last class. So in the active mode, the emitter base junction is forward bias, right? Emitter base junction is forward bias, and the collector base junction is reverse bias, right? Forward bias. This is forward bias, and the collector base is reverse bias. And you know, in the saturation region, the emitter base junction is forward bias, and the collector base junction is also forward bias. And in cutoff mode, there is no current, so the emitter base junction is reverse biased, and the collector base junction is also reverse biased. So these are all the different modes of operation. So we will see in detail regarding the biasing techniques. So the whatever we have discussed now, so the circuit that we have shown here, that is a kind of biasing which is known as fixed bias, okay. So now we are going to discuss different types of biasing techniques. So different types of biasing techniques. Okay, so we are going to discuss different types of biasing techniques. So at first we are going to discuss something known as fixed bias. So fixed bias, you have just seen it now. So we have a power supply, we have a transistor, and we have RC, and for that we have a power supply which is known as VCC. Okay, and we have a RB, and we have VB, and it's going to ground. Then this biasing technique is known as fixed bias. Okay, so we have to take two loops that we have seen in the last slide, and we have another loop here. Okay, loop 2. Okay, and this is loop 1. Sorry, this is loop 1. Okay, it's loop 1. Now, you know, in the loop 1, if we are writing the KVL, we got IB equal to VBB minus 0.7 over RB. Am I correct? And in loop 2, we got VCE in loop 2. Okay, I will use another color. So in loop 2, what we have got? IC, sorry, not IC. In loop 2, we got VCE, which is equal to VCC minus IC RC. And how do we find IC? IC is equal to beta DC times IB. So these are all the basic equation in the case of fixed bias. Okay, these are all the basic equation, loop equation in the case of fixed bias. Now we will see what is the problem with this biasing technique. So we will see a problem. Okay, so question: determine the Q point for the circuit shown below. Okay, and the transistor is having beta DC which is equal to 200. Okay, now the transistor circuit is given, which is having some RC. Okay, the value of RC is 330 ohm, and there is a power supply which is VCC, which is equal to 20 volt. Okay, 20 volt, and this is RB, and we have VBB, which is given 10 volt, and RB is also given, it is 47 kilo ohm. Okay, now we will see how to write the loop equation. So if you are writing the loop equation for loop 1, you can find IB, as we explained before, as VBB minus 0.7 over RB, which is equal to 10 minus 0.7 over 47 kilo ohm, which is equal to, you will be getting something as 198 microampere. Micro is 10 power minus 6. Okay, then you can find IC, which is equal to beta DC times IB, which is nothing but 200. Yes, 200 multiplied by 198 microampere, so which is equal to 39.6 milliampere. Now we will see what is the situation with the loop 2. So from loop 2 we will be finding, so from loop 1 actually we got IB and we got IC, and now we are seeing loop 2. Now from loop 2 we can get what is VCE. Okay, now we are going to find VCE. So you can take the loop 2. So in the loop 2 we will start from VCC. So this is minus here and this is plus here, so it is minus VCC, right? You have already seen this, so I am not going to explain. You can refer to the previous slide. Okay, so it is nothing but minus it is nothing but we can get VCE. VCE is equal to VCC minus IC RC. So what is VCC? VCC is 20 and IC, you know, 39.6 milliampere into RC. RC is 330 ohm, isn't it? So you will be getting it as 6.93 volt. So this is known as VCE, right? So we got VCE, and also we got something known as IC. Okay, we got IC also. Now we are going to draw the load line. So I will include some part in the question also. Draw the load line and mark the Q point. Okay, so we got the Q point actually. So Q point means VCEQ and ICQ. So what is our Q point? So we got IC is equal to 39.6 milliampere and VCE, which is equal to 6.93 volt. This is actually our Q point, because this is your actual current and voltage across the transistor. So this current and voltage for the transistor, we will call it as Q point, because your transistor is operating with this voltage. Now we will draw the curve. So first of all, I will draw the characteristics curve for the transistor alone. So this is for the transistor. You know, the x-axis is VCE and the y-axis is IC. So this is the characteristic curve of the transistor. So this is the characteristics curve of the transistor. Now we will consider this equation. Let's say this is equation, let's say this is the first one. For IB is equation 1 and for IC it is equation 2. Now you can say this is equation number 3. So we will consider equation number 3. Now in the equation number 3, actually you can see this is the x-axis and this is the y-axis, right? Y-axis. Now you can see the equation number 3 is a equation for straight line. So we need to draw a line, but for drawing a line, you know that we need at least 2 points. So our x-axis is VCE and y-axis is IC. So we will find what is x-intercept and what is y-intercept. Okay, so we will find the x-intercept first. Okay, to find the x-intercept, we will take the equation VCE equal to VCC minus IC RC, and you know that this is our x and this is our y. So to find the x-intercept, you will put y equal to 0. So if you put y equal to 0, that means you are going to put IC equal to 0. When IC is equal to 0, we will get VCE equal to VCC. So we got 1 point, right? So we will see, we will mark the point when IC is equal to 0. So this is the region where IC is completely 0. So we will mark here somewhere, that is VCC, that is VCE is equal to VCC. So we got something. Now we will see another part, that is to find the y-intercept. To find the y-intercept, that means x-intercept means if you are drawing the line, this I have already explained, you have to find this x-intercept. This is the x-intercept. Okay, now for y-intercept, nothing but we need to find y-intercept. So for finding the y-intercept, what you will do, you will put x is equal to 0. So what is X here? Your X means VCE. So put VCE equal to 0. That means 0 equal to VCC minus IC RC. So put VCE equal to 0. So you are putting VCE equal to 0. So what is Y? This is your Y, right? So that is IC equal to VCC over RC. So now you got this point. Okay. Now we will see. We can find the y-intercept somewhere here. So we got some point, and this point is VCC over RC. Now you can draw the load line. Okay, you can draw the load line. This line, which is known as load line, it is a straight line, and you have to find the Q point. Okay, and VCC, you know, VCC is given as 20. Am I correct? VCC is given as 20, and this value you will be getting, this is 20, so you will be getting this as 20 divided by RC. RC is 330, that is equal to 60.6 milliampere, and this is nothing but 20 volt, as you know. Now, so you will be getting 60.6 milliampere. Now we have to mark the Q point. How to mark the Q point? So we have to mark the Q point here. You can see the voltage is 6.93. So this is 20 volt. So this voltage is 20. So we'll mark here on the x-axis some 6.93. And you can draw the line, and it will be meeting here, and you will be getting the corresponding current, and the corresponding current is 39.6 milliampere. So 39.6 milliampere. So this is your Q point. That means Q point is 6.93 volt and 39.6 milliampere. Okay, I hope that this is clear. Now this kind of biasing, actually we will be calling it as the fixed bias, but there are a lot of issues related to this kind of biasing technique. Okay, so this kind of biasing technique, actually it is not stable. Okay, now in this problem, actually you have seen whenever the beta was 200, you got IC as something like 39.6. I think it's, am I correct? Yeah, it is 39.6, and VCE is equal to 6.93 volt. Now suppose you are taking the transistor, you have the transistor circuit, and your transistor was in upper half, for example, during the cold climate, and beta DC was 200. Okay, the beta DC was 200. Now you take this transistor to Riyadh, okay, during a hot climate. Now in Riyadh, the same transistor will have beta DC, maybe for example 220, because the beta of the transistor will change with the temperature. This is one of the main issue. So in Riyadh we will calculate actually what is the value of IC and VCE. So what is IC? IB will not change because IB is depending upon RB and VBB. So we are not going to change VBB and RB. So the only thing will be IC. So IC is beta DC times IB. Now instead of the old beta, we'll be using new beta. So if you take the transistor to Riyadh during a hot climate, okay, so it is 220 into 198 microampere. So let me calculate this, how much is the value, and I will tell you. So it is something like 220 into 198. Okay, so it become 43.560. So you can see the new IC So the old IC I will call this is IC1 and this is VCE1, my old values. So new IC, that is IC2, is 43.56 milliampere. So you can see the IC has increased. So whenever whenever beta increases, IC also has been increased in fixed bias. Okay, now we will find what is VCE. VCE is VCC minus IC RC. So we will use our new IC, which is known as IC2. So we will find VCE2. What is VCC? VCC is 20 minus 43.56 milliampere into, it is I think it is 330 RC. So how much you will be getting? So you will be getting 20 minus, that is 43.56 multiplied by 330 ohm. So you will be getting it as something like 5.6252 volt. So this is VCE2. So you can see our VCA also changed. So this is the one of the main issue. So previously the VCE and IC has taken some value for the value of beta as 200. Okay, now currently the beta has been changed to 220, and now you can see the value of IC, also the value of VCE has been changed. That means that your IC, that means that your IC will change with respect to beta. That means whenever beta DC changes, it will cause IC to change. Since IC is changing, it will lead to the change in VCE. So whenever beta DC increases, then what is happening to IC? You can see IC also increases. Then what is happening to VCE? VCE is decreasing. Am I correct? Yes. So this is what happening. Now we will see what happens to our load line. The load line will not be changing, but the Q point has been changed. So let us assume this is our transistor characteristics. So with this transistor characteristics, we have drawn the load line. You remember the load line, this is a 20 volt and this is something around 60.6 milliampere. Okay, and our previous load line was something like 6.93 volt, and the IC was 39.6 milliampere. So this is our IC, this is our VCE1 for beta equal to beta DC is equal to 200, and this is our IC1 in the case of beta DC, which is equal to 200. Okay, this was our previous current. So maybe I can say it is in Abaha, for example. This is the case in Abaha. But now when I take the transistor to Riyadh, what happens? The beta has been increased. That means beta changed from 200. So beta DC changed from 200 to beta DC changed to 220, for example. So what happens? Whenever beta DC changes, you can see the the voltage become 5.6252. Okay, it has reduced. So it is somewhere here. This is your new Q point. This is 5.62952. I think it's 5.6252, right? Yeah, 5.6252. So this is the case with beta DC is equal to 220, or I can say that this is VCE2, new value. Okay, and this is in Riyadh. Okay, this is. Now you can see what happens to our IC. The IC also has been increased. Now IC will become, you can see the IC become 43.560. So IC become 43.560, and this is IC2 in Riyadh. Okay, so this is what happening. You can see that the transistor has moved more to the saturation region. You know that for a transistor, actually this region, that whatever we are calling here, that is the active region, and the region that is known as here, this region, actually this is the cutoff, and the region that is something this region, actually that is known as the saturation region. Okay, so we have to maintain our operating region in active mode. So whenever the beta changes, you can see that the Q point has been moved. Okay, and moved from the point, this point, to, and it has been moved to a new point. Okay, and this is known as, this phenomenon is known as thermal runaway. Okay, thermal runaway. That means the thermal runaway is more in the case of fixed bias. That I can say that the fixed biasing has more change in IC and VCE with respect to change in beta DC. How the beta DC is changing? Beta DC is changing because of the temperature. Okay, so the beta DC is changing because of the temperature. So this is one of the big issue. So we will calculate how much percentage changes will be there for beta DC. To calculate the change in percentage for IC, this is nothing but you will take the new value minus the old value, sorry, IC1 divided by IC1 into 100, and you know what is your IC2. IC2 is 43.56. okay, 43.56 minus 39.6 divided by 39.6, and all are in milliampere. Okay, all are in milliampere, so there is no issue. So into 100. Okay, let me calculate this, and it comes to be 43.56 minus 39.6 divided by 39.6. This is 10. That means 10%. Okay, you can see there is a 10% change in IC. Now we will see how much is the change in VCE. VCE in percentage, delta VCE. That is, we can say it is nothing but VCE2 minus VCE1 divided by VCE1 into 100, which is equal to, what is VCE2? VCE2 is nothing but, VCE2 is nothing but, so we will see VCE2 is 5.6252. okay, 5.6252 minus 6.93 divided by 6.93. okay, so we will see how much it will be the percentage. 5.6252 minus 6.93 divided by 6.93. okay, this is equal to, you will be getting minus 18.89%. so you can see that the change in IC is positive, but the change in VCE is negative. What does it mean? What does it mean? So it means that the IC has been, it means that whenever beta DC increases, it increased the IC. That means this is positive change, and VCE has been decreased. We will call this as a negative change. So we now conclude that our fixed bias is having more change, right? So that is the has large variation in IC and VCE with respect to change in beta. Am I correct? Change in beta DC. So this is one of the important conclusion that is the fixed bias is having a large variation with respect to large variation in IC and VCE with respect to beta DC. So it is not a good biasing technique. So our conclusion is that the fixed bias having thermal runaway and the fixed bias is not a good biasing technique. So I conclude that the fixed bias is not a good biasing technique. Okay, this is the conclusion. Okay, this is the conclusion. Okay, I hope that this is clear. Assalamu alaikum wa rahmatullah.